me and Burak. I'm Alison, and we're going to have Burak talking about Skribe, which is a tool for fuzzing Arbitrum style smart contracts. So for the outline of this presentation, we're just going to give a brief overview of the Arbitrum chain, what is Stylus and why it matters, what Skribe is, and some technical overview, plus a demo of the tool, and a bit of some information on how Skribe works under the hood and the next challenges that we have to face in order to make Skribe better. And yep. So about the Arbitrum chain and ecosystem. Some of you might not know, but Arbitrum, you might not be familiar with the Ethereum L2s. Because of Ethereum high gas cost and the limitations on throughput, people started to create alternative methods to facilitate the usage of blockchains, and that's where L2 came around. Basically, some added mechanism on top of a L1, which is a chain like Ethereum, in which you can process transactions and submit proofs to the chain with optimistic rollups, which is the case of Arbitrum. So you make transactions cost less, and you are able to process more transactions. In its current state, Arbitrum has the top TVL of all L2s available, and the third highest market cap. And any blockchain, any protocol that you have available for Ethereum, it's very likely, as a rule of thumb, that you have that available for Arbitrum as well as another few other L2s. So next slide. Arbitrum allows you, it has a couple of interesting features. One of them is the segmentation for specific use cases of the blockchain itself. You have, let's say, 3 ways of looking at the Arbitrum chains. You have the Arbitrum 1, which is the flagship close to traditional blockchain. So if you are familiar with Ethereum, the implementation of Arbitrum 1 would be the closest for you to understand. You have Arbitrum Nova, which is another different implementation, but it's supported in the same stack, but offers you lower costs in cost of trust. There are different algorithms to process your transactions when you're handling Arbitrum Nova. Then there's Arbitrum Orbit, which is a way that you can implement other L2s and L3s even on top of the Arbitrum stack. So this stack is implemented using Nitro, Arbitrum Nitro, which powers the processing, the full life cycle of a transaction, from sequencing to validations to state changes and everything that is related to the life cycle of the transaction in Arbitrum. Within Nitro, you will find ArbOS. You can go to the next slide. You'll find ArbOS. And ArbOS, the update number 32, introduced actually a new VM to the ecosystem. So before, within Arbitrum Nitro, you only had the EVM, the Ethereum Virtual Machine. And with this update, the WASM VM was introduced. And that was a big change because now you can have languages that compile to WASM, and you can support them as smart contracts. You can generate smart contracts from these languages because you can compile to WASM. And that's where Stylus comes in. So as mentioned, Arbitrum now has an execution engine for WASM smart contracts, and specifically for Rust, a couple of traits have been introduced in which you can implement smart contracts in Rust with some support to interactions with the blockchain itself. It's important to highlight that these two virtual machines, the EVM and the WASM VM, they are feature equivalent. They are interruptible, actually. You can have Solidity smart contracts that have been compiled for the EVM interacting with WASM smart contracts, which is one of the great powers of this new language integrations, and allows you for language agnostic interoperability, which now you can have a myriad of languages to develop smart contracts for the same ecosystem. Because of the Rust capabilities, you are, and the WASM also features, you are open to better performance on smart contracts and lower gas fees for computation. You have at your availability the power of rest safety, not only type safety but also memory safety, and the high level expressivity that you have for Rust smart contracts now. And this strategy aims also to bring different ecosystems and developers of different backgrounds, provide a easier way for them to come into the Arbitrum ecosystem and become smart contract developers as well. So just for a example of a Arbitrum Stylus smart contract in comparison to a Solidity one, this is the traditional, the easier, the introductory counter smart contract. You can see on your left the Solidity version of that smart contract, and the equivalent version of it in Arbitrum Stylus. Of course, it seems a little bit more lengthy, but you have to take into account the expressivity of Rust. So for even larger smart contracts, you might have an easier time expressing what you mean with the business logic of the protocol into the smart contract. This is just for a high-level introduction and overview of what Arbitrum Stylus is, and which leads us to Skribe. So we didn't have any tools for testing in Skribe, and now we do, thanks to Burak.
Yeah. Do you want to continue, or I can take over?
Yeah, you can take it. I just wanted to introduce you.
Yeah, thanks. So Skribe is our property testing and fuzzing framework for Arbitrum contracts, specifically for Stylus. It's like Foundry for Stylus contracts. It supports both Rust and Solidity, and independent of the implementation language of your contracts, you can rust your tests in Rust or Solidity. And Skribe is under the hood using formal semantics of EVM and WASM that we widely use in control and in commat. And Skribe also supports Foundry cheat codes, because Arbitrum's first language is Solidity, so the ecosystem is already familiar with Solidity and Foundry. We support most of the Foundry features. And you can also check out our docs from this link. And let's start with the technical overview. As a first step, you can install Skribe via our package manager kout. You can run kout install Skribe, and it's a Nix-based package manager. It will install Skribe with all the dependencies. And if you want to install a specific version or maybe a pre-release version, you can specify the version with the branch name. And when you install Skribe, you step into your test contracts directory and run Skribe build, which will compile your test contract, and then you can run fuzzing with Skribe run. Skribe run discovers the test functions in your test contract, which they start with tests _ prefix and run them with random inputs. And this is a simple test function, test contract. Again, as in Foundry, also in Skribe, we implement our tests in contracts. And optionally, you can have a setup function, which sets up some helper accounts, some initial blockchain state, and you can also deploy other contracts from your test contract. In this example, by reading the WASM binary file of the counter contract, we deploy the contract and save its address to the contract storage. Then we have a test function. In this function, we have a random argument. It first sets the number by calling the set number endpoint of the counter contract, and then checks if it is correctly sets the variable. Now let's start with the demo.
So just for my understanding, it will run the setup function first, and then from that state run the test function, or?
Yeah, exactly. It runs the setup function first, and you can also have multiple test functions. They will be all executed after running the setup function.
But all of them only from, you run the setup, and then kind of from that state, all the tests are executed, not one after the other.
We run the setup function and we get an initial state, and then we run test functions separately. Each run starts from the initial state created in the setup function.
So it's similar to Foundry in this way.
Exactly. So now you should see my VS Code window. So in this example, we will test a traditional ERC20 style contract. And this is our test contract. In the test contract, we first start with declaring the interface for the contract that we want to test, which is ERC20 interface. So Stylus SDK has this macro for declaring Solidity interfaces. And inside this parenthesis, we have the declaration for the interface. It has these functions. For example, you can check the decimals. You can check the balance of an account. You can transfer tokens. And here we have the test contract, test ERC20. Inside the setup function, we first want to deploy the ERC20 contract. To do that, we first read the binary file of the contract, which we have the path here. And this will gives us the deployed bytecode of the contract. So to deploy that contract, we need to create an init code for it, which is a constructor that returns the bytecode of the contract we want to deploy. To create that init code, we have an helper in the Skribe library, which basically takes the bytecode as a byte array, and then it creates an EVM bytecode that returns the bytecode that we provided. And then by using the deploy function provided by the Stylus SDK, we deploy the contract, which internally calls the create host function, which corresponds to EVM's create instruction. And then we get the address of the deployed contract, and then we save it to the storage of the test contract. And then we have a test function. In this function, we want to test when we have enough balance, we can perform transfers. We have an address parameter here. This is the receiving account, and we have the initial balance of the sending account, and here we have the transfer amount. So we first, from the cheat codes interface, we first call the assume cheat code. We checks that this specifies the preconditions on the arguments we passed. When running the test with fuzzing, these values will have random numbers, and if they don't satisfy the assumption, they will be discarded. So our assumption is that the amount is positive and the amount is less than or equal to the balance. So from the storage, we read the address of the ERC20 contract, and then we create the interface. This will allow us to type safely code this contract. And then we mint the initial balance for the test contract. The test contract will be the sending account. And then here we have an assertion. We ask the balance of this contract, and we assert that it should be equal to the balance. And then we check the initial balance of Alex. It should be 0 because we just created the token contract and we haven't minted tokens for Alex. And then here we perform a transfer to Alex. The amount is the amount of tokens. And after that, we check that the balance of the contract is balance minus amount, and the balance of Alex is amount. So let's run this test. We first need to compile it with Skribe build. To execute Skribe, you need to be in the same directory with your test contract. So here we are in contracts, test ERC20, run Skribe build. And under the hood, it runs cargo to build their test contract. And then we call Skribe run. So it will look at the wasm bytecode of the contract and extract the ABI of the contract. Then it will list all the test functions. After running the setup function, it will run the test functions with randomized inputs. The initialization setup takes a bit long, unfortunately.
Can you tell what's happening inside the initialization phase?
Yeah, in the initialization phase, it takes the wasm of the test contract. This is the first thing. And then it creates an initial K configuration and executes some commands on that configuration to initialize the test contract, which is creating the account for the test contract and setting up its bytecode, and then it calls the setup function of that account. And then eventually it creates a K configuration that we will use as a base initial state. And then at each run, starting from that initial K state, we call the test function with randomized input. For generating random inputs, we use the hypothesis library. Yeah, here, by default, it runs 100 times, but you can also specify different numbers, and you can also specify which test you want to run. Or you can just see the help text. It will show you the available arguments. Let's try to break this test. Here we have the amount. We have the assumption that the amount is less than the balance. So we have enough balance. But let's comment out this line and build the contract. Run the test again. Let's see if it can find a counterexample.
Can you scroll down a little bit in the source code?
Yeah, yeah.
Because if I'm not mistaken, there's already like a combination of input parameters that should make this test fail, right? When the when Alex address is the same as the self contract address.
Yeah, exactly. But since fuzzing
It was not able to find
is
that.
not able to find that example, it's very low probability. It just creates random bytes for the address. It should match the test account's address. Then you are right, this assertion should fail. And also this one. Yeah, here after 3 runs, it has found a counterexample. You see the amount is greater than the balance. Yeah.
That's nice. I like the output.
Now that's the end of the demo. If you don't have any questions, I can continue with the slides and more technical details about the implementation.
So here
Yeah.
we were showing that we can test Solidity smart contracts from Rust now, and using basically kind of the full features of Foundry. And we have access to all the cheat codes. Is that the case, or?
Yeah, not all the cheat codes are implemented, but we have assume, we have expect revert, we have
So kind of the most
some
common
kinds
one.
of assertions. Yeah, and crank.
Mhm. And then are we able to test the WASM smart contracts from Solidity as well?
Yeah, exactly. That's also possible.
Nice.
And also, it's ideally you can directly run your Foundry tests with Skribe. It should run without any issue, unless
And
you use some cheat code that we don't support yet.
Yeah, and the supported cheat codes on the WebAssembly and on the EVM side, are they the same set or are they different set?
Well, they're a bit different. Some of them are not yet implemented, and some of them are not possible at the current state of the Stylus SDK.
Okay. So the Solidity side will still have more complete support for cheat codes then?
Yeah, because we directly use the control semantics. It has access to almost all cheat codes implemented there. Yeah, I will continue with the internals of Skribe. So it's built on KEVM, which is the K semantics for the EVM, and we have KWASM. These both semantics are actively used for other projects. KEVM is used in control, and also KWASM is used in different projects like Casimir for multiverse X and Comet for Stellar. And we also use control semantics for the implementations of the cheat codes. And on top of that, we add Stylus specific semantics, which are Stylus host functions. If you're not familiar with WASM, host functions are the functions that allow you interact with the blockchain from the WASM code. And also some glue semantics for the interoperability between EVM and WASM. That's the semantics part. We compile the semantics and we get an interpreter. And then on the CLI part, the test driver is implemented in Python using PIC and hypothesis. PIC is the library for interacting with k-semantics, and hypothesis is a property-based testing framework. We use it for generating randomized inputs. So here I have a pseudocode for describing how it works from the high level. We first load the binary of the test contract, and then we also load the API of the test contract. Then we set up a k-config from test contracts WASM code. And by the way, I said WASM, but this can be EVM as well. And internally, this will run the setup function. And here we create a template configuration where we have a variable in the k-cell, which we will embed our commands for executing test runs. And we get the test functions from the ABI, the functions that start with test prefix. And then we fuzz the template config with the test ABI strategy. The ABI strategy reads your function signature and create random call data for calling that function. Yeah, we had some challenges during the project. So our first dependency is a diamond dependency issue. So KVM depends on K, KWASM also depends on K, but their K version is pinned to a specific version. So that's the first issue we encountered. And also there was a silly issue because of this combination. In KEVM, we had some instruction names that are capital Ks, and then they, and in KWASM semantics, there were some variables with the same identifier. So we had to change the variable names in KWASM. That's the limitation of K. Yeah, that's the end of the presentation. We can take questions.
I mostly was wondering what else is planned for Skribe, or what could be planned for Skribe to improve usability or access to developers, stuff like that.
Yeah, first of all, we need to work on the Foundry cheat code support. So Stylus developers also has the same capabilities as the Solidity developers. That's the first thing. And another update would be on the WASM semantics. So since we developed the WASM semantics, the WebAssembly specification had new updates, like new instructions and new features. So we also need to keep up with those developments on that side. And also, since we are in the ecosystem, we can integrate Skribe with symbolic debugger, so that from the VS Code screen you can debug your WASM execution, WASM and EVM. Yeah.
Nice. Okay. So some performance and usability improvements, and then also maybe just developer experience improvements as well.
Can I use this Skribe tool on like a pure Solidity code base that was written for Ethereum mainnet as well?
Yeah. Ethereum mainnet, I haven't tried it, but it should work.
So it can even, like, it will automatically be able to compile it?
It calls forge under the hood, so it should be compiled without an issue.
Okay,
Mhm.
interesting. So this also, like, as a side effect, this also brings fuzzing to control, right?
Yeah, that's a good point.
Is this all open source, or is it closed source?
Yeah, it's fully open source. You can build it from source, and you can hack it.
It's nice.
Well, thank you, Barak, for the presentation. I think at this point
You're
we can
welcome.
probably stop the recording.